Okay, so Unit 3 was the dosage calculations. You should have those tests back or should be getting them back soon. Make sure you do corrections on those. And if you're not sure on any of them, please let me know. I'll try to help you through them or work together with each other if you want to. I do want to make sure that you know how to do each of those problems. So even if we have to take a half an hour or something at some point in class before the end of the semester and go over some of them, please let me know if you're struggling with any of them. I want to make sure we do that. So Unit 4, we're going to be talking about graphing and some more algebra and relationships. This is a unit we've put in here for a couple of reasons. When you go to analyze data, which is going to be our next unit, and statistics, you have to be able to display it graphically. Also, many of you, well, at this point, I think if you're going to go on to be a registered nurse, I believe I don't know if it's changed yet or if it's in the process of changing, requiring a bachelor's degree. So at any rate, many of you will most likely go on to a bachelor's degree where you'll have to take a college algebra course. And this section is hopefully to prep you for that a little bit. So what we're looking at is representing our numbers. And we talked a little bit at the beginning of the course about representing numbers on a number line. And there was a couple of different ways that we represented them. One way that we represented them, if you're dealing with integers and negative numbers, is you can represent numbers with a vector. Like the number 4 would be an arrow that starts at 0 and goes to 4. While negative 4 starts at 0 and goes to negative 4. And if I draw my number line out to scale here, those should be the same length, just pointing in opposite directions. That is a working definition. If we're going to use those numbers for something, for calculations, that's a great way to represent them. For example, 8 plus 3. Well, yeah, you have a vector for 8. Have a vector for 3. And you put them together, they get 11. But if we're just looking at displaying several values, that's a little bit of a cumbersome way of doing it. A little bit briefer, more efficient way of representing those values is to just put a dot at the location of their value. So 4, instead of being that arrow, would just be a dot at 4. 8 would just be a dot at 8. 3 would just be a dot at 3. So that represents those values. Well, most of the time, a single value is not terribly useful. Its relationship to at least one other value is what's important to us. So most of the time, we need to display two values and how they're related to each other. So I might have the number 3 and the number 7. Now what I just wrote there is called an ordered pair. Ordered because the order does matter. The first one, being positioned first, makes a difference compared to being positioned second. Pair, obviously, because there's two numbers. If I wanted to display those two numbers graphically, I mean, it would be possible to do it on a number line. I'm just going to display the positive end since those are both positive. And I can display both the 3 and the 7. If I wanted to show that they're being linked together, it's a little more difficult. And there's several ways to do it. I suppose I could do an arrow like this, showing that the 3 is first and the 7 is second, which would be okay if there's just a couple of pairs of numbers. But if I have more than a few of these pairs, that number line would get cluttered very, very quickly. So the solution to displaying these numbers in their relationship to each other was developed by a man by the name of René Descartes. You don't need to know the name, but it is called the Cartesian coordinate system. And what he did was he took that original number line and left it just like it was. Positives going to the right, like always. Negatives going to the left. And he said that's going to display the first number in our ordered pair. For the second number, he created a second number line, and it went the other direction. The 0 is at the same spot as the 0 on the first number line. Positive numbers going up. Negative numbers going down. So now to represent that pair we had, 3, was it 3, 7? Yeah, 3, 7. Well, we said the first number of the pair was represented by that horizontal number line. So 3 would be right in here. The second number is represented by that vertical number line. The 7 would be right here. To express, now what I've just put there is not really the points themselves, just kind of their location on the number line. The actual point was found by projecting them out to where they run into each other, where they intersect. That brown point there is the point that represents both of those numbers. It is called the coordinate of those points. So now we said the first number is always represented by this horizontal number line. That is what is often referred to as the independent axis. Some just call it the x-axis because it is usually the variable x that is used for it. Most of the time, though, in medical applications, it's not an x, it's a t for time. Time is almost always represented on that x-axis if we're looking at the passage over time. The vertical one is what's called the dependent axis. Or often just referred to as the y-axis because the variable y is often represented on that axis. So first of all, I need to explain the difference between independent and dependent. Independent means it can vary on its own. It changes either naturally over time, like if it is time, it changes naturally as the progression of time. Or if it's other things like age, well, age I guess would be time too. For comparing height to weight, you know, it's the variable we want to look at kind of as the cause. So if we want to look at the height, we'd most likely put the height on the horizontal axis, and then the weight would be the effect. I mean, looking at being taller, you're most likely going to weigh more. If it's time, passage over time on the horizontal axis, and you might be looking at administering medication. The amount of medication administered would be the effect on the vertical axis, on the dependent axis. So anyway, up here in our coordinate, as we said, the first coordinate is that independent variable, that horizontal variable, generally labeled with the letter x. And the second coordinate is the vertical, generally labeled with the letter y. Where the two axes intersect here is called the origin. The origin is actually a very important place on the graph. If we were to spend more time in graphing lines and other shapes, the origin kind of means beginning or starting point, and that's exactly what it is. All of our different graphs actually originate at that point, and they're moved around the graph from there to their final position. It's also the 0 point for both axes. So it's where both axes really start and go out from there. Quadrants, not terribly important. I will never test you on what quadrant something is in, but this is called the first quadrant here, mainly because both x and y are positive, and in real life, that's where most things occur. Now we go around counterclockwise, so that'd be second, third, and fourth quadrants. The main reason we go around counterclockwise is because from some of our other conventions, and when we do navigation and stuff like that, we proceed around the compass counterclockwise in our directionals and things like that. So it's more than tradition. Realistically, the ones that get used the most, first quadrant gets used a lot, everything's positive there. And then the fourth quadrant, your time or whatever is still progressing in a positive direction, but you can drop into negative values. So let's plot some points in here and see how everything fits in. Well, I'm going to put them on here and have you tell me the coordinate. Let's do that. What would the coordinate of that point be? Well, we start out with the horizontal first. What point is it at on the horizontal here? 8. And on the vertical? 3. So that would be 8, 3. This point here. Perfect. On the horizontal, it's at -4. And on the vertical, it's at 6. So -4, comma 6. How about this one? Okay. On the horizontal, it's at -6 here. On the vertical, it's at -9. So -6, -9 is that coordinate. How about this one? 4, -5. Good. On the horizontal, it's at 4. On the vertical, it's at -5. A little bit trickier. What's that point? It's at -3 for the horizontal. Vertical, it's at 0. Perfect. How about this point? Perfect. On the horizontal, it's at 0. Vertically, it's at 5. So when they're on one of the axes, one of the coordinates is going to be 0. If it's on the x-axis, it'll be the y-coordinate is 0. The vertical coordinate is 0. If it's on the y-axis, it's going to be the x-coordinate, the horizontal coordinate is 0. Well, one of our purposes of going over these graphs is not just to display data over time, but to display relationships, mathematical relationships. We've solved equations in the past. We might have solved equations like 3x plus 2 equals 11. And we solved it by subtracting 2. You get 9 equals 3x. And then dividing by 3 to get that 3 equals x, or x equals 3. If I have the equation 20 equals 3x plus 2, it looks very similar. In fact, if we go to solve this, the steps to solve this are exactly the same. I'd subtract 2 to get 18 equals 3x. 2 is gone. And then I would divide by 3 to get 6 equals x. And there are an infinite number of equations out there where I can just put a different number here and get a related equation that's solved using the exact same steps, but I get a different result for x. Well, I can represent all of those equations with just one. That whole family of equations, it's called, where everything's the same except for the constant on the other side, can be represented like this, as y equals 3x plus 2. And I can solve that whole family of equations all at the same time. Or I can at least display the solutions for that whole family of equations all at the same time. And the way I'm going to do that is with a graph. In order to graph it, though, I'd have to figure out where to put this on the graph and what shape it's going to be. So to do that, I start out with a table. Now remember we said x was the independent variable. So what that means is I can pick whatever values I want to for x. Now I'm going to pick some negative, some positive, kind of scatter them out across the graph. So I might do -3, -1. 0 is always an easy one to use, so I'm going to put in 0. +1 and +3. That gives me kind of a nice even spread. If I'm looking at my graph here, gives me some points that are kind of spread out across it, right? We said y was the dependent variable. The reason for that is now that we have selected values for x, the value for y is completely determined. It depends on the value of x. The formula, once we know x, the formula determines the value for y. So y is going to be, if x is -3, y is going to be 3 times x, or 3 times -3 plus 2. It's determined by this formula. So all I did there is I replaced the x in the formula with the value I chose for x over here. Now I go ahead, if I calculate it out, 3 times -3 is -9, plus 2 is a -7. So that's giving me an ordered pair. X is -3 when y is -7. So I can put a dot here at -3, -7. Right there. Or close to it. So then the next value I chose for x was -1. So now we have to figure out what y has to be if x is -1. So I replace x in my equation with -1. So 3 times -1 plus 2. 3 times -1 is -3. Plus 2 is -1. So when x is -1, y is also -1. So x is -1, y is -1, gives me a point right there. If x is 0, 3 times 0 plus 2. Well, 3 times 0 is 0, plus 2 is 2. So when x is 0, y is 2. Gives me an ordered pair. Oops. So x is 0, y is 2 is going to be right there. X is 1, so 3 times 1 plus 2. Well, 3 times 1 is 3, plus 2 would be 5. So when x is 1, y is 5. So 1, 5. And final value, and at this point I can see it forms a nice straight line. If my graph is a little straighter, it would be perfectly straight across my graph. But let's do the last one just to be sure. So x is 3, so 3 times 3 plus 2, which would be 11. So when x is 3, y is 11. So 3, 11, right up there. Like I said, if I'd done a good job of creating my graph, I can't even draw the line through the points right now, apparently. It makes a nice straight line through my graph. Pretend that's straight. So the question always comes up, how do I know what numbers to choose here? And the answer is I don't. I just picked numbers that were kind of spread out across the graph. You know, -3, -1, 0, 1, and 3. And I figured once I got those points on the graph, I could either figure out what the shape looks like or at least figure out where I need to know more information. Let me show you what I mean by that. So I'm going to graph one a little bit more complicated. Let's say I have y equals x squared plus 5x plus 6. So I'm going to use -3, -1, 0, and so on again. But I'm going to make sure I give myself plenty of room to calculate. So I'm not going to write them all in quite yet. So if x is -3, y is determined by this formula again. So -3 squared, x squared becomes -3 squared, plus 5x becomes 5 times -3, plus 6. So I'm going to do my order of operations now. -3 squared is 9. 5 times -3 is a -15, plus 6. Well, 5 minus 15, or sorry, 9 minus 15 is -6, plus 6 is 0. So that's giving me, when x is -3, y is 0. So -3, 0 is right there. Let's try if x is -1. So now y would be -1 squared plus 5 times -1 plus 6. -1 squared would be 1. 5 times -1 would be -5 plus 6. So 1 minus 5 is -4 plus 6 is 2. So when x is -1, y is 2. So -1, 2 is right there. Let's try 0. If x is 0. Now if x is 0, y is going to be 0 squared plus 5 times 0 plus 6. Well, 0 squared is 0. 5 times 0 is 0. Plus 6 is 6. So when x is 0, y is 6. So x is 0, y is 6. Well, even with just those 3 points on there, it's become pretty obvious this is not going to be a straight line. Now if I try the point, put in 1 for x. X is 1. We've got 1 squared plus 5 times 1 plus 6. Well, 1 squared is 1. 5 times 1 is 5 plus 6. 1 plus 5 is 6 plus 6 is 12. So when x is 1, y is 12. So 1, 12. We're off the graph. So it doesn't make any sense to use x equals negative or +3 here, because at +3 it looks like it's going to keep going way up in here. We won't be able to graph it anyway. Do we know enough to graph this right now? Not really. But I do know, it looks like over here, it's climbing off the edge of our graph. So I need to know more in this area. So I need values of x that are smaller than -1. So maybe I'll use -2 and maybe -4 here. See what I get for those values of x. You see what I did there? I used the points I already had. I just guessed at these points here. Put them on the graph, and then I use them to determine where I need to find more points to figure out what the graph looks like. So I'm going to try x is -2 and x is -3. So let's start with -2. If x is -2, we're using the same formula again. y is negative 2 squared plus 5 times negative 2 plus 6. Negative 2 squared is 4. 5 times negative 2 is a negative 10 plus 6. 4 minus 10 is negative 6 plus 6 is 0. So if x is negative 2, y is 0. So x is negative 2, y is 0, right there. We said x is negative 4 is the next one we're going to try. So if x is negative 4, got negative 4 squared plus 5 times negative 4 plus 6. Negative 4 squared is 16. 5 times negative 4 is negative 20 plus 6. 16 plus negative 20 is negative 4 plus 6 is 2. So I have, when x is negative 4, y is 2. Would seem to be right about there. I'm starting to get the picture, but let's go one more. Let's do x is negative 5 over here and see what happens. So if x is negative 5, y is negative 5 squared plus 5 times negative 5 plus 6. Negative 5 squared is 25. 5 times negative 5 is negative 25 plus 6. But of course, 5 minus 25 is 0 plus 6 is 6. So when x is negative 5, y is 6. So negative 5 and 6. Now it's becoming more apparent that our graph looks something like this. So picking those points and plotting them on the graph is not a guarantee that you're going to get the shape. You'll have to pick more points to figure out what that shape is. There are a lot of different shapes that we could graph. I'm going to do one more here. It's going to look like this. Y equals x divided by 4. Actually, that's not y. But y equals 4 divided by x, sorry. Now, when we go to pick values for x, sometimes we've got to look at the equation and decide if there are values that are going to be easier than others. If I used a negative 3 for x here, it wouldn't work real well. Because 4 divided by negative 3 is, well, negative 1 1/3. So instead of negative 3, I'm going to use negative 4. I'm going to get my graph ready to go over here. So, if x is negative 4, y is 4 divided by negative 4, 4 divided by x, get negative 1. So x is negative 4, y is negative 1, right there. Let's try negative 1 for x. If x is negative 1, 4 divided by negative 1 is negative 4. So x is negative 1, y is negative 4 is right there. What if x is 0? Y would be 4 divided by 0. What's 4 divided by 0? That Well, if you try that in your calculator, it's going to give you domain error or error. You can't do it. We cannot divide by 0, which means x cannot equal 4. Or x cannot equal 0, I should say. You can't divide by 0. So let's try some other numbers. If x is 1, y is 4 divided by 1, which would be 4. So if x is 1, y is 4. Well, definitely not a straight line. If I use a positive 4 for x, y will be 4 divided by 4, which is 1. So when x is 4, y is 1. Right now my graph looks like a rectangle. Obviously not enough points. I know that we have issues here at 0. X cannot be 0. So let's figure out what happens in the middle here, like right in here, and then out here. The same here, in the middle and then out here. So it's 4, so let's use 2 and maybe 8 and see what happens. So if x is 2, and we'll use 8. If x is 2, y is 4 divided by 2, which is 2. So that'd be 2, 2 right there. If x were 8, y would be 4 divided by 8, which is 0.5 or 1/2. So at 8 and 1/2. So that's what, 5, 6, 7, 8, 1/2 would be somewhere out here. We're starting to get a picture of a curve like that. On the other side, if x were -2 or -8, we're going to do these both at once. Y would be 4 divided by -2 or -2. So that would give us -2, -2 again. If x were -8, it would be 4 divided by -8 or a -1/2 or -0.5. So that's -8 and -0.5. So we'll plot those. We had -2, -2 right there, and -8, -0.5. So we get curves like this. Now, most of the time to us, what's really interesting is where x is positive, so it'll be this side. This is actually called a decay curve. Some medicines decay like this in the body, where every period of time the amount of medicine in the body gets cut in half or whatever. Alcohol metabolizes that way in the body. It's not a linear metabolization. It's the more alcohol that's in your body, the faster it metabolizes, but as it decreases, it slows down. Okay, so we can graph those. Excuse me. Does anybody have any questions on creating the tables and plotting the points on the graph? It's basically an exhaustive plot process. You just keep picking values of x and plotting them on the graph until you've got enough points that you can figure out what it looks like. Okay. Well, we want to focus in now on special shapes. One of them is a line. The first thing we need is we need to be able to figure out when an equation, when a graph is going to be a line. Well, if we look at what we did up above, we had y equals 3x plus 2. We had y equals x squared plus 5x plus 6. And we had y equals 4 divided by x. The only one of those that formed a line was this one here. This one has a power on the x. In fact, a power on any variable is bad. Anytime there is a power on one of the variables, other than 1, because technically this is a power of 1 and that's a power of 1. Anytime there's a power on any of the variables other than 1, it's not going to be a line. This one here, we divided by x. Technically, dividing by x is x to the power of a -1. So it's kind of the same as the first one. It's a power other than +1 on the variable. Now, one equation that we didn't take time to graph might look like this. Y equals 2 to the power of x. If I were going to graph that, well, 2 to the power of 0 would be 1. If x were 1, 2 to the power of 1 would be 2. If x were 2, 2 to the power of 2 would be 4. If x were 3, 2 to the power of 3 would be 8. Get the point. If x were -1, 2 to the -1 is 1/2. If x were -2, 2 to the -2 is 1/4. Looks like that. An exponential curve. It's a growth curve. If you look at population growth, they usually take a curve like that. They double every so many years. Bacteria cultures and stuff like that in the lab usually have growth curves like that. So for this one, the variable is a power. Because of that, that is not a line. So you can tell here that generally what makes things not lines on our graph is going to be powers. The presence of powers connected to our variables, to be specific. Is that going to form a line on our graph? Well, does it have any powers on our variables other than 1? No, that's just y or y to the 1. That's just x or x to the 1. Am I dividing by either of the variables? Nope. Are either the variables a power themselves? Are they in the power, like 2 to the x? No. So because it does not have any of those 3 things, that will be a line on the graph. This one here, will it be a line on the graph? Well, it has a power in it, doesn't it? But is that power connected to the variables? No, that's 5 to the 3rd power. That's just 125. Does y or x have a power on them? No. Are either one of them a power? No. And are we dividing by either one of them? No. That will form a line on the graph. How about this one? Will that form a line on the graph? No, we're dividing by x. 2 divided by x, that will not be a line. How about this one? No powers on either variable. Neither variable is a power. Not dividing by either variable. That's going to be a line. How about this one? There's a squared on the x, isn't there? That will not be a line. This one, y equals the square root of 7x. It looks like it doesn't have any of those things. It looks like it's something we haven't talked about yet. But a square root is a power. If you recall when we did order of operations, we defined exponents. Exponents are both powers and roots. So that root, the x is inside the square root. So that is a power on our variable. So no, that is not a straight line. So now that we know what lines are going to look like on our graph, or what equations are going to look like that form lines. Now we can look at zeroing in on how to graph them, or shortcuts for how to graph them. So let's start out with a simple graph here. And I'm going to start out with the simplest linear equation I can think of. That's y equals x. No powers on either of the variables, not dividing by either variable. Neither variable is a power. If I pick values for x, it's going to be really easy. I don't even need to draw out the table, do I? If x is -3, what's y? -3. If x is 0, what's y? 0. If x is +2, what's y? +2, right? Because y equals x. If I plot those points, I get a line that runs corner to corner across my graph. Notice it goes through the origin, goes through the middle of the graph. Well, that was the simplest possible equation I could make. What are some things I could do that would make it more complex? Well, I might add or subtract or multiply or divide. Let's try y equals x plus 2. So if I pick values for x, if x is 0, what's y going to be? Well, what's 0 plus 2? 2, right? If x is 0, y is 0 plus 2, which is 2. If x is -2, what's y going to be? 0, yeah. -2 plus 2 is 0. If x is 3, what's y going to be? Well, 3 plus 2 is 5, right? We can see by those points what we get here is a line that's parallel to the first line. It goes across our graph at the same angle. The only difference is it is moved up 2 spots, the +2. Well, with that in mind, can you predict what would happen if I tried to graph y equals x minus 3? Well, let's try it. If x is -3, well, what is -3 minus 3? That'd be -6, right? So if x is -3, y is -6. If x is 0, what would y be? Well, 0 minus 3 would be -3. If x were 1, 1 minus 3 would be -2. So if x were 1, y is -2. So now it's a line that looks like this. Again, it goes the same angle. It's parallel to that first line. It's just moved from the origin. It's moved down 3. So adding 2 moved it up 2. Subtracting 3 moved it down 3. So we can move it up or down by adding or subtracting to the x. What if we multiply x? Y equals 2 times x. Well, now if x is 0, y is 0. It's back to going through the origin again. If x is -2, what's y? Well, 2 times -2 would be -4. So if x is -2, y is -4 down here. If x were 3, 2 times 3 would be 6, so y would be 6. So x is 2, y is 6 up here. We get a line that goes through the center again, through the origin, but now it's steeper. It's got a steeper angle across the graph. So multiplying the x makes the line steeper. How do you think I'd make the line shallower then? Divide. Now, from our fractions, we learned that dividing by a number is the same as multiplying by its reciprocal. So rather than dividing by 2, we're going to multiply by 1/2. So y equals 1/2 times x. That's the same as y equals x divided by 2. So now if x is 0, what's y? Still 0. 1/2 times 0 is 0. If x were -4, what's y? Well, 1/2 times -4 would be -2. So if x is -4, y is -2. If x were +4, what's y? 1/2 times +4 is 2. So +4, +2. And yes, it does make that line go shallower across the graph, a less steep angle. But it does go through the center again. So far now, all of these lines, as we move from left to right, have gone up on our graph. How do you think I'd make a line go down? Let's try multiplying by a negative number. If x is 0, of course, anything times 0 is still 0, so it still goes through the center. If x is -1, what's -3 times -1? +3. So -1, +3. If x is a +2, -3 times +2 is a -6. So y would be -6. So that does give us a line that angles down across our graph. So really, there's only two things that can happen to a line on our graph. From the center of the graph, it can move up or down, and the angle can get steeper or shallower. So if I were going to graph y equals 3x minus 1, the -1 tells me that instead of starting in the center, I move down 1. I start out down 1. The 3 multiplying the x tells me this is going to be steeper than normal. Well, the moving up or down from the origin is pretty definite. -1, you move down 1 space. +3, you move up 3 spaces. The 3 multiplying the x, making it steeper or shallower, is a little bit vague at this point. So let's focus on that for just a minute. That number that multiplies the x is called a slope, the angle at which it goes across our graph. Slope is always a fraction. It is a rise over a run. Now you might be looking at 3 thinking 3 is not a fraction, but it is. I can write it as 3 over 1. So the rise of the vertical is 3, the run is 1. So what that is saying is from that starting point, now this was our starting point, 1 unit down from the origin because of the -1. We're going to rise 3, 1, 2, 3, and run 1, right there. I can keep going if I want to. Rise 1, 2, 3, run 1. And that's my line through those points. So if I am given the equation y equals 2/3 x plus 3, on my graph, where am I going to start? Well, I always start by what's been added or subtracted. The +3 means I go up 1, 2, 3. That's my first point, is right there. 3 units above the origin. The 2/3 is a slope. Remember, the top number is a rise. The bottom number is a run. So from this starting point, I'm going to rise how many units? 2. Now I'm going to run 3. There's my second point. If I wanted to, I could have, from that point, I could have rose 2, run 3, and another point, if it makes it easier. So this is the slope. This starting point here is called the Y-intercept. It's where the line intercepts, or intersects, if you prefer that word, the y-axis. We've reached the halfway point, so let's go ahead and take our break. We'll come back more. We'll talk more about graphing lines. Then we'll look at slopes and rates of change and some other stuff.